Thank you. My name is Jaakko Juntunen. I'm from Optenni Limited. This is probably about the 10th or 12th time I'm having a presentation at this event. But every time something new. So this time my topic is RF front-end receiver matching for carrier aggregation. And I think that the topic as such is very increasingly more important in the future. I will talk a bit more about what's going on. First, a few words of Optenni and our software product, Optenni Lab. We call it or position it as an RF design automation framework, and somehow the emphasis on the word automation. So we create or synthesize lump matching circuits, microstrip matching circuits. Multi-port matching is very important, very non-trivial thing. Broadband, multi-band, tunable and switchable designs. So these examples are mostly related to antennas. And as Optenni name somehow bears within the kind of connotation to antennas, this is like our classical application domain is related to antennas. But today's talk and presentation is about something which is kind of related, but not exactly on antennas, but the receiver thing, because it's very similar problems anyway. So for us, or in our terms, the RF design automation, we can say that it's circuit synthesis-based solutions to challenging problems, be it broadband, multi-band, multi-port tunable, for antennas, amplifiers, and filters, the most like a classical RF devices. It also can be applied to whole RF chains. So in the end of the day, many times the designer's challenge, especially system integrators' design challenge, is to make the system performance as good as possible. And the beef here is that we automate dull work, repetitive design tasks, and outsource that to software. And so this way, we can call that the software is kind of a virtual assistant that you can let, okay, I want to have say, 100 or 200 topologies to be optimized and sorted. It's a bit the same idea what Malcolm was pointing to in his presentation, that there's more and more automation for the design work itself. And we have quite long history in doing that. And so we have good experience on what are the tasks that you can let safely the software do and where the designer needs a special attention. And you can say that actually with such a design automation, the junior designers can provide senior results. And that's why senior designers don't always like us, because then the juniors are the same level. But we say that the seniors are then world-class designers, and that is kind of maybe the way forward. Applications, antenna matching. Here, the second bullet, LNA matching, especially the carrier aggregation, because it changes everything. It's basically not big deal to match an LNA for single band, fine. But what happens with carrier aggregation is very interesting. A little bit about the landscape, our technology partners. So we are, of course, in the center of the world, but we have lots of both software and hardware links to other ecosystem players in the RF design domain. So let's start from the left, measurement equipment. So we provide links like live VNA connection to, let's say, most available VNAs on the market. We are linking with, say, several electromagnetic simulators used in the RF and microwave. We have obviously a link to microwave office, which is very convenient. Say the software interfaces are really useful and well exposed and well documented. We utilize vendor libraries when we create the synthesis. So we directly operate on the real models. And we have compatibility with tunable components used especially in antenna tuners, like from Weiss-Pry, Corvo, Cavendish Kinetics. So coming to this presentation overview, what is like the problem that I want to describe and what we can provide to solve that problem. And like a simplified receiver diagram could be something like this, that we have an antenna, the receiver antenna, then we have a switch which dynamically switches between different branches, which is called carrier aggregation. So for those who are not working exactly on that topic. So when there is a high download rate required at any point in time, then the switch can choose like 1, 2, or 3, for example, parallel bands being received at the same time. And this way multiplying the amount of data that can be downloaded. And so this challenge will become more burning with 5G applications. I think currently the maximum number of parallel co-carriers is, I think it's 5. And there are lots of visions that increase that number. It sounds simple. Why not put 30 bands in parallel? Easy said, very difficult to do. We consider in this presentation an example. I just rather arbitrarily was picking from a document like one specification or request for downlink carrier aggregation considering band 3, band 7, band 20. If we first look at the non-carrier aggregation mode, so they are on one at a time. This is relatively simple problem if the switch is good. So the isolation of the switch is important. Another important thing from our perspective is that we can use the real switch model. So we don't have to assume ideal like isolation or ideal insertion loss. We simply just take the switch model and then we see what happens and then we optimize. Then it's not so easy to find like acoustic filter models from public sources, but there are a bunch, initially EPCOS designs actually that you can just download. And I was using such like a publicly available models. I have no idea if they are the latest and greatest, but anyway, they serve the purpose of this demonstration. As a switch model, I use Infineon single pole 4-throw, like a multi-stage or multi-throw switch. I'm using only 3 bands, so I'm using this switch in redundant mode and just not use one of the throws. And so this set of components is not specifically designed for this particular carrier aggregation application. I think this is not necessarily the most practical setup. This is more challenging setup, that if you just take some filters and try to guarantee that they work together. I think it probably goes, there are more professional like filter designers in the audience. I think that the filters can upfront be designed to serve a given constellation in the carrier aggregation. As an LNA, I use an Infineon application node that is available in the microwave office as well. And that choice is mostly based upon model availability and the frequency coverage. Okay, so with microwave office, for example, you can easily check for each of the bands which are the optimal noise, like input gammas for the LNA. So they don't vary vastly, but a little bit anyway. And basically the switches and the filters are all matched to 50 ohms. So why not check what happens if we just look what we get. And so behind this symbol, in microwave office, I'm having like 3 different states for the switch, throwing one branch at a time. Just to see that how they work together. No matching circuits anywhere. And so it seems like this is reasonably okay. So the noise figure is relatively flat, relatively. The gain, some ripple, yeah. But anyway, nothing like catastrophic. So this, in a non-carrier aggregation mode, it almost works like this. Of course, the question, can it be improved somehow? And for Optenni Lab, this is of course the point of the tool, is to design then improving the chains. And so in practical perspective, we import all the switch states, now in this case 3 different states, and then we assign, like we call frequency configuration. One of the switch states is called RFC to RF1. And there we assign the optimal input gamma for the respective node, the second node in the system, and then an insertion loss target for the through path, for the S21. So port 2 is now the band 3 node. And repeat this for the nodes 3 and okay, this is like band 3, band 7, and band 20. And the beauty here is that we don't have to assume too much in advance what kind of matching circuit potentially works. We can insert black boxes, or synthesis blocks as we call. So we have the second node here. This is like the second throw branch of the switch. And then we say that, okay, 0 to 2 components on each side of the filter. And then we click OK. And then we get lots of topologies. And it has turned out that in such applications, many times that like the performance metrics is about the same for quite many in the list. And we can quickly pinpoint that here we have a particularly simple one where we have just on one side of the filter the matching section for the band 3. Band 20, it turns out that it's advantageous to have, like this is like a simple circuit that comes out. And for band 7, similar topology than for band 3. This is not necessarily so intuitive. And you could spend a lot of time seeking these topologies. So how should you know that this filter benefits in that kind of topology? Trying out. Maybe there could be some like theoretical reasons to favor this or that. But then you have anyway like an unknown factor, which is the switch. You have designed you know how your filters work, but then there is something non-ideal in the switch itself. So this is now more or less a push-button solution. Okay, so we have a transfer circuit to microwave office where we can add the LNA model, and we can calculate then the noise figure, for example. So at the moment we don't calculate it yet, so it's planned downstream. So if we compare this no matching circuit with the matching circuit, we see that especially the gain ripple is smoothened quite a bit. So the dashed lines are with the matching circuits. And so now the question, we know the answer, but it's kind of a fair question that could we use, now we have like a working solution for non-carrier aggregation. What if we attempt to use that in carrier aggregation? What happens? And the issue is that the LNAs get typically catastrophically mismatched. So we have non-carrier aggregation. The optimal point is here, non-carrier aggregation, and if we have all three branches on at the same time, this is how the gamma in looks like. But there is a worse problem, equally bad or even worse, is that the simple impedance mismatch, the insertion loss drops catastrophically, very dramatically. And so in this case, just blindly applying the same matching circuits causes like up to 15 decibel degradation in the noise figure. So it's just useless. Just showing one quick example on the software. So here I have this green box here in the middle is the switch, now with the state of all branches throwing. And I have put just some small resistors such that I can kind of dynamically switch them, like each branch is on and off. But if we have, let's say, the filters connected here, especially for band 7, this is the insertion loss. Band 20 looks good, more or less. Band 3 looks medium, and band 7 looks bad. So it's minus 15 dB insertion loss. And the main reason is perhaps that it's so severely mismatched. If we look at the Smith chart plot, here it's more darker color is showing the different frequency bands. So band 20 is quite well matched, while the band 7 and band 20 appear close to the short circuit. And if I'm tuning, for example, one of the resistors, so what if I put, say, I more or less cut the branch for, this is for band 3, this is for band 20, and this is, now we have only band 7 kind of there. So we can see that the insertion loss is reasonable, but if we put the band 20 in parallel, this alone, having these two branches in parallel, is causing so very severe mismatch and very severe drop for the insertion loss. Okay, so this is actually the point where we actually really enter the stage. And like a useful, rather than say brute force, you can attempt brute force, but if you have several carrier aggregation branches, several filters, several black box, it's too much, it's exponential problem. While it's like a practical approach is to first design the filters on the branches, kind of anti-matching them to the enemy bands. I don't know what is the right term. Sometimes they are co-carriers or something like that. But for this behavior perspective, they are like enemies. And we'd rather like to map them to open circuits. If we see open circuit for band 7 and band 20 at the band 3 branch, then these bands don't interact, and you can combine them. And this definition, this fits very well the way how Optenni Lab works. And this is why this is a fair application for Optenni Lab. And maybe I just show a second demonstration where I'm having, this is now only the band 3 filter model. And if we look, I have put markers on the co-carrier frequencies. So this is band 7, and this is band 20. So we see that it's rejecting okay, especially band 20. It's very close to the Smith chart, but the phases are relatively arbitrary, unless they are designed up front. But in my case, I just took the filter that I could get. So now the challenge is to make sure that while having good match for band 3, simultaneously to map band 20 and band 7 to open circuits. Then we have a structure that is invisible to those other bands. And so if we look the setup, this is how it looks like. Black box, 0 to 3 components, frequencies. This is the insertion loss target for band 3, and then I have what we call impedance target, where I specify that while looking towards the LNA, I have the band 7 downlink, and my design target is open circuit. And then we have weight factor with which you can balance, like what is the most important goal. Same thing for band 20. And when I click OK, so let's do the synthesis now. So Optenni Lab is now going through, first of all, there are from 0 to 3 components on each side. And so there are only the number of components can be like quite many combinations, 0, 0, 0, 1, 1, 0, 1, 1, and so on. And for example, 3, 3 expands to very many topologies. And so this is now exactly the virtual assistant who is doing the job. It shouldn't take more than like 1 more minute, but sometimes it may take a while. You can do other things while your like a trusted assistant is doing extremely dull work. That's for sure. And we can monitor what is the best cost function value so far. And then we get like a ranked list where we can try and, let's say, pick like the shorter here, the fewer components. And then we have like a certain, of course they are not in the same measure, the insertion loss and the impedance target. So, but anyway, there is like a combined cost function value, and we can notice that, okay, this very simple circuit here has actually pretty nice cost function of about as good as the top performing. And if we look, let's look at the S11 only. Select plot items. So this may tell the story well. So this is the same as we had previously. This is the target, pure open circuit, and these are now band 7 and band 20, how they are mapped close to the open circuit, while band 3 is still quite okay in the middle. And this happened in less than a coffee break. And because the search is reasonably exhaustive, it's not strictly speaking exhaustive, but say, compared to what anybody would do manually, it's exhaustive. We know that we are not missing any essential topologies. And then we can, like with Edgar's presentation, then you can sketch, this might be actually quite okay, so the values are reasonable. Of course, you can set limits up front, so on. So this is exactly the way how we get like the first shot. I pre-arrange the filters to work together. And then I'm assuming a relatively, I know the switch is quite good. And then we just put everything together and re-optimize. So the targets, the specifications get more complicated, like the threefold carrier aggregation involves the target for good insertion loss for each branch, but the desired noise impedances while looking towards the antenna node. And that for all carrier aggregation combinations. But other than that, other than this setting, it's just selecting topology orders and pushing the button. This is the first shot, like re-optimizing the values, and let's look. We get the noise match pretty good. So in this graph, for example, we have the 3 different carrier aggregation states. No carrier aggregation in blue, B3 and B7 in green, and in red, all 3 together. And almost intact, almost insensitive from the LNA perspective, which means the LNA is well matched, irrespective of the switch state. And the insertion loss, also pretty good. So nothing as catastrophic as we saw before. And gain, more or less the same conclusion. Some further practical considerations. So we started with ideal components. It's usually a good way to get somewhere. And because we historically can use also lossy, non-ideal components in the synthesis, why not use them here as well? And we can incorporate EM layouts, for example, for the external matching circuits that might be there. And for demonstration, we use 2 Murata libraries, say 0204, sorry, 0201 inductors and capacitors, which are like commonly used in the industry. But from the design and button pushing perspective, it's similar otherwise. I just choose to use library components. And there is no pre-guarantee that the topologies would be similar. They might be like a non-ideal enough. Or, as the tool suggests, for example, series resonator circuit, where like the self-resonance frequencies and all that play a role. If I would just replace the values of these components by ideal equivalence, it would not be the same thing. So what I got is a long list of topologies. I spent quite a while letting the assistant working, say, over lunch, or that's no problem. Then I go through the list and identify interesting, most simple ones that I could possibly identify, and found this one. The libraries know the tolerances, so we can right away run tolerance analysis on them as well. So just showing, here. So here, this is the outcome. So we can see it's like a first of a long list of more complicated topologies. Because of the losses, the ranking might be such that the simpler topologies are better. Less components, less losses, kind of. And here I can select so this is now insertion loss view. If we look like band 3 alone, now non-carrier aggregation for band 3, same circuit, nothing changes here, only the switch position or switch state changes. Band 7 here, band 20 there, B3, B7, or all. Not bad. Like the tolerance analysis, we take just there are now 5 switch states, and so the tolerance analysis run over all these states, so it might take a moment. And we can actually rank also the results looked through the sensitivity, tolerance sensitivity analysis. So these are like, then eventually we get the result and the degradation due to the component tolerances. And then it's possible to identify which one is most responsible for the spread in the results and so on and so forth. Okay, let me just come to close to the conclusion. So with library components in this example, I observe between 0.2 and 1 dB degradation in the noise figure. This is like less so for band 20 for whatever reasons, bit more severe for band 3. But we have lossy components, they had their contribution. Okay, conclusion. So we considered like it's agreeable, simplified architecture, but kind of realistic, kind of non-trivial because it's threefold, very difficult to doing the acrobacy otherwise, how to handle the cooperation between the different bands, and here we can automate that. And vendor library components, that is important. Also not considered in detail, but indeed we can incorporate the EM. For example, you can take Axiom simulation of the matching circuit layouts and use them in the ports and synthesize the components on like a component, so-called component ports. Right. That's it for today.